Justin Miller, Octal College Physics here. We have got some things to do, so let's just get started. At this point, we want to introduce some sort of expression that allows us to determine the force of interaction between charged particles. So we're going to stick with point charges and say, well, what is the magnitude of the force that they exert on one another? And the direction we'll deal with as well. So to this, we look at Coulombs Law. Coulomb after Charles Coulomb, Coulombs Law. Says that the magnitude of the force of interaction between two point charges Q1 and Q2 that are separated by a distance R is given by magnitude of the force of interaction. F hat is equal to K sub E multiplied by the absolute value of Q1 multiplied by the absolute value of Q2 divided by R squared. So Q1 and Q2 are the charges, and the reason that we're taking the absolute value is because charge could be positive or negative, right? So we want to make sure that we're just treating them as the absolute values here, because again, this is just the magnitude. Magnitude should be positive. We've got R, the distance that these charges are separated by, and then we've got K sub E. K sub E is Coulomb's constant. K sub E is equal to 8.987 times 10 to the 9th Newton meter squared per Coulomb squared. Generally, we'll just use 8.99, three significant figures. That's fine. 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. And there we go. So we got these two charges, Q1 and Q2, separated by a distance R, and this expression here would give us the force that one of the charges exerts on the other. And notice that it doesn't state which one we're talking about. It's an interaction between two charges. Forces come in pairs. The force, in terms of its magnitude, is equal between the two. So it's like I push on something, it pushes back on me with the same amount of force. That's what we have with these two charges. So let's go ahead and draw something out here. We can have our, say, some Q1, and we can have some Q2. There's our two charges, point charges, very discrete, localized charges, and they are separated by some distance, R, straight line distance between them, and that's it. If we want to know the magnitude of the force, we just have to know, hey, how much charge is here, how much charge is here, and what's that distance of separation. We can go ahead and quantify what the magnitude of the force is. In terms of the direction, that's where you have to be a little bit careful. That's determined by the charges in question, which charge you're looking at, and how the charges are oriented relative to one another. So the first thing that we want to know when we're trying to discern what direction is the actual force is what charge you want to be looking at. Do I want to look at the force that Q1 exerts on Q2 or the force that Q2 exerts on Q1? That's going to hinge on what direction we get. And then we've also got, hey, is it an attractive force between the two charges under consideration, or is it a repulsive force between the two charges under consideration? And then how are the charges arranged spatially with respect to one another? So this is kind of the simplest case, but we can still start to draw some stuff out. Say that we wanted to know the force that Q1 exerts on Q2. Well, we ask ourselves, We want to know the force on this one. Is the force between these two charges attractive or repulsive? Oh, they are opposite charges. They're attracted to one another, right? Opposites attract. So the force that Q1 exerts on Q2 is like this. And I could call that F12 hat. Force that Q1 exerts on Q2. So notice that is that way. Whereas if I said, no, you know what, I actually want the force that Q2 exerts on Q1, well, I draw that force in and say, oh, that is that way. F21 hat. So this force Q2 exerts on Q1, and this force that Q1 exerts on Q2. And what should we note? The magnitudes of those forces are equal. F12 hat magnitude is equal to the magnitude of F21 hat is equal to K sub E times the absolute value of Q1 times the absolute value of Q2 divided by R squared. Equal magnitudes, but notice opposite directions, right? Yeah, that's it. Equal magnitude, opposite directions, forces of interaction. Forces come in pairs. So when we just want the magnitude, this is all that we need to consider here. The charges and the distance of separation. But if we want to be more definitive, like, hey, what is the actual direction to? We have to say what's charge and attractive or repulsive. And then we can geometrically determine what the composition of the direction of that vector actually is. So the direction of the force between two charges depends on which charge is being considered. Whether the force is repulsive or attractive. And the spatial orientation of the charges. The direction of this force will always be aligned with the straight line between the two charges. So this straight line, it's imaginary, but there's the shortest distance straight line between the two charges. That force must always lie along or aligned with that particular straight line. So let's look at a couple little cases here. We'll do a couple problems. So let's drop a little coordinate system so we have some way of gauging some things. Let's do 2 dimensions, x, y. I'm gonna take 2 charges. I'm gonna take one charge and say we've got a charge here, plus charge. We'll call that Q1. And then I'll take another plus charge. We'll call that Q2. And we'll just ask, hey, what is the direction of the force that Q1 exerts on Q2? All right, well, the direction of the force we're considering on the charge Q2. And then it comes into, is a repulsive or attractive force regarding the other charge? Well, they're like charges, so it's a repulsive force. These 2 charges are pushing each other away. When we're considering this one, pushing it away is in this direction. F hat 1, 2, direction would be positive J hat, assuming that they're one at the origin and one on the y-axis. If we went ahead and said, well, what about the force on Q1? We'd have this. F hat 2, 1, directionally would be negative J hat. Opposite directions, right? So we're able to specifically say the directions in a case where we have a standardized coordinate system and we know how the charges are arranged relative to one another, and we know what type of charges they are. Plus, 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 minus, minus, minus. That's it. So we can do all sorts of stuff, and pretty much that's what we want to get out of this. Take a minus charge there, take a plus charge there. We can call this Q1, and call that Q2, and then say, well, what is the force that Q1 exerts on Q2? What is the direction of it? And this is, again, where you have to be a little bit careful. The direction of it would be, well, it's attracted to Q1. They're opposite charges. So the force on Q2 would be this way, which would be F hat 1, 2 would be in the negative I hat direction. Shorten that up a little bit. Whereas if we looked at the force on Q1 due to Q2, we would have that 2 is attractive, and we'd have that this is F2, 1 hat. It's the positive I hat direction. So it turns out in this particular orientation that force on the negative charge is in the positive direction, and the force on the positive charge is in the negative direction. What would happen if we switched the order of these? If we said that this was positive and this was negative? Well, we would still have that the forces would be this way. Negative I hat on this one, positive I hat on that one, but we've changed which one's which. So that'd be it. So ultimately, this is what you've got to be aware of. What are the charges being considered? How are they arranged with respect to one another? And go from there. All right, so this brings up a good time to go ahead and do a little problem involving some point charges. And we'll do a couple just to see how this all plays out. So, we'll just use this. So, yeah, here's the problem. All right, so we got ourselves 2 charges, Q1 and Q2, and we're going to draw them on the board and go ahead and start to ask, what is the force on each charge? So let's just draw up a little scenario here. We've got Y, we've got X, and we'll keep this first one highly simple. Actually, let's do like this. Say we've got minus charge there, plus charge there. We'll call this Q1. We'll call this Q2. And then we need to make some quantifications and say where these actual charges reside. So we'll say that Q1 is going to be equal to 7 microcoulombs. So that's micro there, 10 to the negative 6. You're going to see this a lot because a lot of times we're utilizing very small amounts of charge. Micro comes into play all over in this course. So we didn't really use it too much last semester, if at all. It's all over the place here. So get used to it in micro, 10 to the negative 6. So microcoulombs, 7 microcoulombs, and actually, because it is a negative charge, go ahead and throw a negative sign in there, don't forget that. And we'll say that this charge is at the origin, 0, 0. Great, we'll go ahead and say, what about Q2? Let's say Q2 is going to be a positive charge, and we'll say that it is 9 microcoulombs. It's a little bit bigger, that's fine. It's at a different location, and we're going to say it's at 0, and then we'll call that negative 0.7, negative 0.6, negative 0.6, and that's going to be in meters there. So they're 60 centimeters apart. Fantastic. All right, so first question. What is force exerted on Q1? So that's for the force. That implies magnitude and direction. So we want to know, hey, what's the magnitude and what's the direction of the force on Q1? So what do? We just go ahead and say, well, we want the force that Q2 exerts on Q1 is going to be equal to K sub E. Again, this is absolute value of this. K sub E times the absolute value, magnitude, this is absolute value. K sub E Q1 divided by Q2 divided by R squared. Well, what's R going to be? Well, R is just going to be the difference in the y components there. R is always a positive quantity because it's a distance. 0.6 meters would be that distance between those two charges. So we've got R, and we just go ahead and stick this stuff in. So K sub E, we'll just write down K sub E, 8.99 10 to the 9th. And then we've got the absolute value of both of these. Right now I'll be a little careful, but as time goes on, we'll just make it positive. But negative 7 times 10 to the negative 6 coulombs, absolute value, times 9 times 10 to the negative 6 coulombs, divided by 0.6 meters, quantity squared. So there's the magnitude of the force that Q2 exerts on Q1. And we can go ahead and quantify that. That is going to be equal to 8.99. 9 times 6 times negative 6 divided by 0.6 squared. We got 1.573. 1.573 newtons would be the end result there. We've got coulombs times coulombs is coulomb squared divided by meter squared, and then we've got K sub E is 8.99 newtons meter squared per coulomb squared. So the meter squared cancels out, the coulomb squared cancels out, and we're left with newtons, as we should be. So there's the magnitude of said force. We also want the direction. So the direction often will be something that you look at the actual spatial orientation of the objects and figure it out from there. So again, we want the force on Q1. We ask ourselves, is it an attractive force or repulsive force between the two charges under consideration? You say, well, they're attracted to one another, right? Because it is a minus charge here and a positive charge there. So the force has to be down like this. Straight down, and we've got, this would be F hat 2,1. Well, if we know the magnitude, now we can see the direction. It's in the negative j hat direction. So when we go ahead and stick this in, we can go ahead and say then that the actual force Q2 exerts on Q1 is equal to 1.573 newtons. I'm going to make that negative. Throw a J hat there, and there we go. So there's the magnitude, there's the direction. Negative 1.573 newtons J hat. Fantastic. Now, we could also ask, what about the force on Q2? We'll say, what is F12 hat? Well, let's go ahead and think about this. The force of interaction, in terms of its magnitude, it's the same quantities here. K sub E, Q1, Q2 divided by R squared. They're equal distances away from one another, right? So, in the end, we've got this, the magnitude of the force that Q1 exerts on Q2 is equal to the magnitude of the force that Q2 exerts on Q1 is equal to 1.573 newtons. Great, so we got the magnitude. What about the direction? We come back over here to say again, this is a repulsive force. Q2 is attracted to Q1, attractive force. Q2 is attracted to Q1, and we've got F12 hat like that. Straight up, which would be positive J hat direction. So in the end, we go ahead and say that F12 hat is equal to 1.573 newtons J hat. All right. Pretty easy, right? And the answer is, yeah, pretty easy. Just have to get it down. All right, let's look at one more different configuration here and see what we can do now. So what happens if they're not nicely along some axis? And we want to figure out the direction of the force as well as the magnitude. So we'll draw another diagram here. We take two charges, y-axis, x-axis. Let's do something semi-simple. We'll take one still at the origin. So we've got the positive one at the origin. Plus we'll call that Q1. And then we'll take a Q2. We're gonna have Q2 be negative. And I'm gonna put it up here. Let's put it like right here. Negative. There's Q2. We'll say that Q1 is, let's stick with the same amounts. We've got, no, we changed the order. Let's use different amounts. That's fine. So let's say that Q1 is equal to 5 microcoulombs, and it is at the origin 0, 0, and that Q2 is going to be equal to negative 3 microcoulombs, again because it's negative, and we're going to put it at, let's say, 0.3, 0.7, 0.3, 0.7, and again that's in meters. So now we want to know, again, part A, force on Q1 is equal to a what? Shorthanded things a little bit now. All right, we want the force on Q1. Well, what do we need? We need the charges, we have those, and we need the distance that they're separated by. So these two charges are separated by some distance, which we call R. Well, how are we going to figure out what R is? Well, we can note that we can always make a little triangle with this. Nice right triangle. And what do we have? We have the R is the hypotenuse of this triangle here. We've got some X and some Y, if you will. And what do we have? Well, since this one's at 0, 0, this is 0.3 meters over in the X direction, and this is 0.7 meters up in the Y direction. So this is 0.3, this is 0.7. Thus we have that R squared is equal to 0.3 meters squared plus 0.7 meters squared. The reason I just stick with R squared, because we don't need R, we need R squared. So there it is right there. If you want to compute R then square it, that's fine too. At any rate, there's R squared, and from there we can go ahead and say force that Q2 exerts on Q1 in terms of its magnitude is K sub E, absolute value of Q1, absolute value of Q2 divided by R squared, which is now going to be equal to K sub E times the absolute value of 5 times 10 to the negative 6 coulombs times the absolute value of negative 3 times 10 to the negative 6 coulombs divided by their distance away squared, which is the quantity of 0.3 meters quantity squared plus 0.7 meters quantity squared. So there we go. We can go ahead and get the magnitude from this. And let's just do that. We got 8.99 e to the 9th times 5 e to the negative 6 times 3 e to the negative 6 divided by the quantity, 0.3 squared plus 0.7 squared. 3.7, yes. That's what we said. Good. That was good. Parentheses good. We get 0.2325. 0.2325 newtons. So that seems okay, right? Sure. So what about the direction? Well, the direction, again, you got to look at the diagram here. We want the direction of the force exerted on this charge right here. And we've also got that these two charges are attracted or repulsive, attracted to one another or repelled by one another. The answer is yes, good job. They are attracted to one another, opposite charges. So the force exerted on Q1, sorry, I was pointing up at Q2, force exerted on Q1 is up that way. There it is. So we've got, that is our F21 hat. There's the magnitude right there, 0.2325 newtons. What about the direction? What do we want to call it? Well, generally we want to call it some angle with respect to the positive x direction. That's the easiest way to go about it. So if we look at this composition here with this triangle, there is this theta right there. I'm going to call it theta F1 because it's the theta that corresponds to the direction of the force on charge number 1. So how are we going to get that? Completely geometrically, right? We've got that theta, say F1, is going to be gotten by the arctangent of opposite over adjacent. 0.7 divided by 0.3. And we can go ahead and pop that in. Definitely want to be in degrees. 0.7 divided by 0.3. And 66.8 degrees. So in the end, we've got F21 hat is equal to 0.2325 newtons at 66.8 degrees with respect to the positive x direction. And there we go. You get the direction geometrically. Depends on the orientation, the charge under consideration, and whether it's a repulsive or attractive force between the two charges. So what if we ask one more thing here? I know, just one more though. What is F12? What about the force on this one right there? Well, again, it's the same charges, the same distance of separation. The magnitude of the force has to be the same. So we can go ahead and say, number 1, the magnitude of the force on charge number 2 is equal to the magnitude of the force on charge number 1, which is 0.2325 newtons. It's just a matter of the direction. Well, the direction is definitely different. The direction is down like that. So in this case, this is our F12 hat. What are we going to call that? Again, we want to call it something with respect to the positive x direction. So I'm going to take this and kind of blow it up over here. Just that charge. Help this out. So we're going to say, there's our charge. This is Q2. And roughly, kind of going with this, we've got that the force on it is directed down like this. That would be our F12 hat. Say, how do we want to say it in terms of its direction? Well, we can overlap the coordinate system there and say this is the angle that we want. There is our theta F2 with respect to the positive x direction. So that's positive x. There we go. There's the direction of our force. Well, how are we going to get that? Well, we can note what the direction of this was, right? If I go ahead and take this vector and just sort of translate it up here. Have something for reference here. That was kind of bad. This was our F21 direction. These two forces are just opposite directions, right? And we also had, this was theta F21. And we already know what that is. That was equal to 66.8 degrees. Well, what are we adding onto it? We're going to add this onto it. We've got the angle between the direction of F21 and F12. And this is merely 180 degrees. 180 degrees, opposite direction. That's it, we flipped it by 180, that is opposite. So when we go ahead and say, what is theta F2, direction of this? Well, it is going to be 180 degrees plus 66.8 degrees, which is equal to 246.8 degrees. You can always look at that and say, is that reasonable? Does that make sense? Say, well, that would be 0 degrees, that would be 90, that would be 180. Straight down would be 270. We're in between 180 and 270. Yeah, 246.8 definitely seems reasonable. Just like this one, it's in the first quadrant. That seems reasonable that it's 66.8. It's always good to go back and look. But nonetheless, we've got ourselves this F12 hat. Force that Q1 exerts on Q2 is equal to 0.2325 newtons at 246.8 degrees. If we're doing three significant figures, you can round that up to 247, but I go ahead and keep the 0.8 there. And that's that. So drawing out little diagrams ends up being fairly important, so you can keep track of the directions, and you can always go back and make sure that what you have drawn out matches what you get numerically, because it's easy to make little mistakes. It's really easy to make directional mistakes. It's just as easy to catch them if you're drawing stuff out and then double checking. Hey, yeah, 66.8, that's reasonable. Hey, yeah, 246.8, yeah, that's reasonable. There we go. So we'll leave it at that. We'll come back and do some more problems, but those are some good little problems there. That's it. Take care.